Hi, it's ChemGal, and in this video I'm going to show you how to perform electrophilic addition of HBr to an alkene. To perform any mechanism, we need to have a good understanding of nucleophiles and electrophiles. Below I have a chart we made in another video contrasting the two. If you're fuzzy on this topic, feel free to rewatch it before we begin. I'll put the link down below. So here we have an alkene, which is basically a carbon structure with a double bond. And we have HBr, hydrobromic acid. So whenever I do a mechanism, I like to ask myself, who's the nucleophile and who's the electrophile? And if you recall, we said that acids tend to be electrophiles. And by default, that makes our alkene our nucleophile. And that's really what happens in a mechanism. You got a nucleophile and an electrophile, and they react together. So remember that we also said that we draw the arrow going from the nucleophile to the electrophile. Always. We never draw it the other way around. So this alkene says, hey, HBr, I really like your hydrogen. I think I'm going to take it. And HBr says, sure, but I want some electron density in advance. To start it off, we draw an arrow going from the double bond of the alkene over to the hydrogen. And then we draw another arrow from between the hydrogen and the bromide going to the bromide to show that the bond is breaking between hydrogen and bromine. And if we want to see what our products look like, we know that the bond actually broke for the alkene. So now this alkene became an alkane, which is a carbon structure that has all single bonds. And we know that the bromine lost its hydrogen. And we knew that bromine initially started off with 3 lone pairs, so we can go ahead and draw them in here. And so what happened was it lost its hydrogen, but in exchange for that hydrogen, it gained a lone pair. You might be asking yourself, where did that lone pair come from? And what I like to do when I was learning this mechanism was I like to imagine that this bond here that broke off in the form of a lone pair and traveled onto this bromine structure. Because remember that the arrow shows the flow of electron density. And so you can imagine that that bond broke in the form of a lone pair and traveled onto the bromine. Some people like to imagine this in different ways, and that's fine. Whatever works best for you works. And now what happened to this alkane over here? So this guy actually grabbed the hydrogen. And so we can either throw it onto this carbon or this carbon, since that's where the bond broke. And both these carbons are chemically the same, so it doesn't matter where we put it. Again, both these carbons are the same, so it doesn't matter where we put it. So we can go ahead and throw it onto this carbon over here. Now, what does that mean for the other carbon? Let's go ahead and look at the original structure. We have this alkene here. And if we draw it in expanded form, it actually looks like this. So this is a CH3 group, this is a CH group, CH group, and a CH3 group. And why is that important? That's important because these two carbons here have hydrogens on them. And if we draw it in, we can see what's going on with the hydrogens in the intermediate structure. So we can go ahead and draw them in here. And so those are the two hydrogens that I originally started off with, and this is the hydrogen that came from the bromine. So now what we see here is we threw the hydrogen from the bromine onto this carbon here. So now this carbon actually has 4 bonds, 1, 2, 3, 4. And we know that a carbon with 4 bonds is happy and it's neutral. But what happened to the other carbon? We took away that double bond there, So now it's just left with this single bond, the methyl group, and this hydrogen. So this carbon only has 3 bonds. And if we calculate the formal charge for a carbon with 3 bonds, the formal charge is going to be equal to valence electrons minus surrounding electrons. And so carbon has 4 valence electrons, and surrounding it right now, there is 3 bonds. So 1 surrounding electron from each bond makes 3 surrounding electrons. 4 minus 3 has a positive 1 charge, and therefore this carbon here has a positive charge. So we can go ahead and draw that in. And so carbons with a positive charge get a special name. They're called carbocations. Please do not say carbocation. And so carbocations are very reactive because they have 3 bonds and carbon typically likes to have 4. So they're very good electrophiles. And they're electrophiles because remember we said that electrophiles tend to be positively charged. So we can go ahead and make note of that here. That's going to be our electrophile. And we can go ahead and calculate the formal charge for this bromine atom. So formal charge is equal to valence electrons minus surrounding electrons. How many valence electrons does bromine have? Well, bromine is a halogen, so it has 7 valence electrons. And surrounding it right now, there is 1, 2, 3, 4, 5, 6, 7, 8 because of the 4 lone pairs. And 7 minus 8 gives you a -1 charge. Therefore, this bromine is negatively charged. And we know that negatively charged things tend to be nucleophiles. So we can go ahead and write that in there. And we know that nucleophiles like to do the attacking, right? The arrow always goes from nucleophile to electrophile. So we can go ahead and draw an arrow going from the bromine lone pair over to the carbon that's lonely, the carbocation. And if we do that here, we see that the bromine is going to join that carbocation and make it a carbon with 4 bonds. And I didn't draw in the hydrogens here, but we do know that there is a hydrogen here and 2 here. And so now everyone is happy. All the carbons here have 4 bonds, right? This guy has 4 bonds, and this guy has 4 bonds. So those carbons are great. What about that bromine there? It originally had 4 lone pairs, right? It had 1, 2, 3, 4, 5, 6, 7, 8 surrounding electrons. And so now it actually lost the lone pair, and it only has 3 lone pairs. And that's because it used this lone pair here to make a bond with that carbocation carbon. So it lost a lone pair in making that bond. Because remember that each bond consists of 2 electrons. So I'm going to go ahead and erase these hydrogens here because I want you to get used to looking at them without the hydrogens. And so if we go ahead and calculate the formal charge for that bromine atom, we know that it's going to have 7 valence electrons, and surrounding it right now, there is 1, 2, 3, 4, 5, 6, and 1 from the bond. Therefore, there is 7 surrounding electrons, and 7 minus 7 makes for a total charge of 0. Therefore, this bromine has no formal charge. And so what I want to point out to you here is that whenever you do a mechanism, there's always a conservation of charge. So notice here how we started off neutral, there was nothing charged, and our intermediates had a net charge of 0 because the carbocation was positive and the bromide was negative, so that added up to 0. And our products here have 0 formal charge as well. So you see here how there's always that conservation of charge. And so whenever you add HBr onto an alkene, it always adds across the double bond. So here is where our hydrogen added. And that's the same hydrogen that we added here. I also want to point out to you that your products are going to be racemic. Now what does that mean? That means that your products might look like this. And all that means is the bromine can either join from the front position here, indicated by the wedge, or the back position here, indicated by the dash. And the reason why it has the opportunity to join from both sides is because it's joining a carbon that has a missing bond. So you can kind of imagine it as an open place where it can either come from the front or from the back. And it doesn't matter which one it goes to. So we say here that it has a racemic mixture, meaning that you form both R and S products. And I'm going to get into what R and S mean in another video. So now I want to take a moment to look at what might happen if you're adding HBr across an alkene that isn't symmetrical. So now we know that this guy's our nucleophile, this guy is our electrophile, and we're going to draw an arrow going from the double bond onto the hydrogen and from this bond to the bromine. And so we're going to form this structure here where the double bond breaks and bromine is going to lose its hydrogen. So again, bromine gains a lone pair from that broken double bond. And I can highlight that for you. And it becomes negatively charged. Now we want to talk about where we're going to put that carbocation. Are we going to put the positive charge here or here? And so there's two scenarios that I have drawn down for you below, scenario 1 and scenario 2. So it all depends on where we put the hydrogen, right? Remember that this hydrogen is breaking off and it's going to attach either onto this carbon or to this carbon. So let's figure out what happens in each scenario. Let's say I put the hydrogen here. And in scenario 2, let's say I put the hydrogen here. So what's going to happen here? In scenario 1, if I put the hydrogen on the left carbon, that means that the right carbon is going to get the carbocation because that's going to be the carbon that's missing the bond. In scenario 2, if I put the hydrogen on this carbon, that means that this carbon is going to get the positive charge because that's the carbon that's going to be missing the bond. And we know that because if we look at our original structure here, we see that in scenario 1, it would have had a hydrogen on that carbon and this carbon would have been fine and had 4 bonds. And in scenario 2, if we draw in that original hydrogen, this carbon would have been sad and lonely because it only has 3 bonds, and that's why scenario 2 gets the carbocation positive charge on the left. So now what's going to happen is we're going to add bromine. And bromine here has a negative charge. And so now I have the lone pairs drawn in for you here. And so if we draw an arrow going from one of those lone pairs to the carbocation here, in both scenarios, we're going to form different products. And so the first product is going to look like this. And the second product is going to look like this. Now we have different names for these. The first example, we have what's called a Markovnikov product. And in the second product, we have what's called an Anti-Markovnikov product. And we're going to favor one of these scenarios over the other. We're going to favor the Markovnikov product over the Anti-Markovnikov product. And the reason why is because the Markovnikov intermediate is actually more stable than the anti-Markovnikov intermediate. And we can look at the carbocations to examine why. So in scenario 1, we have this carbocation here. And it has 3 alkyl groups attached to it. And so we say that this is actually a tertiary substituted carbocation. In example 2, we have this carbocation, and it has 2 alkyl groups attached to it. And so we say that this is a secondary carbocation. Now you might be asking, well, isn't there a hydrogen over here coming from the original structure? And yes, there is a hydrogen here. And yes, it does have 3 bonds, 1, 2, 3, But when we're looking in terms of stability, we look at how many alkyl groups it has or how many carbon groups it has. And so it only has 2 carbon groups. And because it only has 2 carbon groups, we say that it is a secondary stabilized carbocation. And so why is tertiary better than secondary? Tertiary is better because the more alkyl groups you have to stabilize that carbocation positive charge, the more stable it is. So this guy is more stable than this guy because it has 3 groups instead of 2. So we're going to say that our major product is going to be the Markovnikov product, and the minor product would be the Anti-Markovnikov product, which you would rarely ever form. So this would rarely ever form because its intermediate is not as stable as the Markovnikov one. So whenever you're answering multiple choice questions about this or questions in general, you always want to assume that they're asking you for the major product, okay? You don't want to draw the minor product unless it tells you otherwise. And I would definitely ask your professor in what case would you want you to draw the minor product. And so whenever you answer multiple choice questions on these, it's safe to assume that they only want the major product. Now here's a multiple choice question for you. What is the major product of the following reaction? And so we can go ahead and draw out the mechanism for this now since we know it very well. And so what we find is this bond breaks. So we went from an alkene, right, to our alkane, all single bonds. And our bromine lost its hydrogen friend. So now it's just by itself, Br minus. Now, where are we going to draw the carbocation? Well, if we put the hydrogen over here, we have to draw the carbocation here. And if we draw the hydrogen here, then we're going to have to draw the carbocation here. Because remember, whoever doesn't get the hydrogen has a missing bond. So which carbocation is better? Is it better to have a carbocation here or here? And so if we put the positive charge here, that would give rise to a primary carbocation since this carbon only has 1 alkyl group. And if we put the positive charge here, that would give rise to a secondary carbocation since this has 2 alkyl groups. So we can go ahead and put that positive charge over here. And so this carbocation has 2 groups here, and therefore it is secondary. So the most stabilized form for a carbocation is to be tertiary. And you can imagine that every carbocation aspires to be tertiary, or at least most alkyl substituted, because the more substituted it is with alkyl groups, the more stable it is. So keep that in mind for this example. Now we can draw on bromine's lone pairs over here. And you might be thinking that bromine is probably going to latch onto that carbocation and form the structure. And so you might be thinking that your answer choice is letter A, but that is a trap. And I'm going to explain to you why that is. And so remember that I told you that carbocations like to be in their most stable form. So if a carbocation is secondary, as in this case, and has the opportunity to become tertiary, it's going to take that opportunity. For now, let's go ahead and erase those answer choices. And so now all I did was I brought this guy down here so we can examine him a little bit. So what we can do in this case scenario is perform something called an alkyl shift. So what is an alkyl shift? And so for an alkyl shift, I want you to imagine that we're taking off a methyl group here and putting it onto this carbon. So I want you to imagine that for a minute. What might happen there? Let's go ahead and move this methyl group here, and let's go ahead and fix the angle of that other methyl group. So we can pull it down a little bit. There we go. So we move that methyl group over there. Now what happens? So let's also draw on the hydrogens we had before. So we know from the beginning that we totally had a hydrogen here. And so we can draw that in over here. And that was the same hydrogen that was here. That doesn't correspond to the hydrogen we added from bromine. The hydrogen we added from bromine added on to the opposite carbon. So remember, this carbon got the hydrogen and this carbon got the positive charge. This hydrogen had been there all along. It had been there from the beginning. So we can go ahead and draw that in over here. So we see here how in the beginning this carbon had 3 bonds, and that's what made it a carbocation. But now it gained this new methyl group from the alkyl shift, and so now it has 4 bonds. So do you think it's still a carbocation? No, right? Now it's happy because it has 4 bonds. If we look at this carbon over here, this carbon had 4 bonds, but now it lost one of its methyl groups due to the alkyl shift. And so now it only has 3 bonds. And so that makes it positively charged. It makes it a carbocation. So when we have an alkyl shift, we shift one of the methyl groups. So we chopped this guy off and we brought him over here. Therefore, our positive charge shifted as well, and it shifted onto this carbon. And so that's how you perform an alkyl shift. And what's the purpose of all of this? Well, if we look at this carbocation, we said here that it's secondary because it has 2 alkyl groups. Remember, we don't count the hydrogens when we're looking for the degree of stability. So this guy, we said, is secondary carbocation. And now if we look at the new carbocation we formed, it has 3 alkyl groups, which means that it is tertiary. And so because it's tertiary, it's more stable, right? Remember we said that the order of stability goes from primary to secondary to tertiary, where tertiary is the most stable. So what's the purpose of all of this? It's to form a more stable intermediate. Because when you have a more stable intermediate, your reaction is likely to run better. And so now if we go ahead and bring in that bromine guy over here, and we add him to our carbocation, what kind of answer are we going to get? So now we see here that bromine is actually going to attach to this carbon over here. And therefore, this structure is going to be our answer. And this corresponds to letter A. So now the point of all of this is to be aware of alkyl shifts when you're doing these problems. So you always want to ask yourself, if I have a primary carbocation, does it have an opportunity to become secondary? If I have a secondary carbocation, does it have an opportunity to become tertiary? And if so, go ahead and perform the shift and then add your bromine to the carbocation. Now here's a multiple choice question for you. What is the major product of the following reaction? And so now you have hydrochloric acid. And don't freak out, chlorine is just like bromine. They react both the same way because they're both halogens. So it's going to be the same exact mechanism. So let's go ahead and start this off. So we grab our hydrogen here and we form our carbocation. Remember to show both arrows in order to get full credit for your tests. So now what's going to happen here? Just like bromide, we formed chloride. Chloride is also negatively charged. And so now we got to form our carbocation. So we know that a hydrogen can either add to this carbon or to this carbon. And that's because those were the 2 carbons corresponding to where the double bond originally was, right? We can't just randomly add the carbocation here because nothing happened to that guy. So if we add the hydrogen over here, we're going to get the carbocation here. And if we add the hydrogen here, we're going to get the carbocation here. A carbocation here corresponds to a secondary carbocation, and a carbocation here also corresponds to a secondary carbocation. So it kind of doesn't matter. But I'm going to go ahead and say that we'll add the hydrogen here and throw the carbocation over here. Now remember I said that whenever we do these mechanisms, we want to ask ourselves if there's opportunity to reach a higher degree of stability for the carbocation. And so we see here that this carbocation has two alkyl groups, one here and one here. And so that makes it a secondary carbocation. So now we ask ourselves, is there room to become a tertiary carbocation? And the answer is yes. And it might not be through an alkyl shift here. Here we actually perform something called a hydride shift. And to examine this, I'm going to go ahead and remove these answer choices for a moment. So what's going to happen here? Well, we formed this carbocation. And now we ask ourselves if there's room to become tertiary, since this guy is secondary. And let's draw in some hydrogens that we had in the beginning. We know that we have a hydrogen on this carbon because it has 4 bonds, and we have a hydrogen on this carbon. So if we draw in those 2 hydrogens here, and I move this positive charge over, and so for this hydride shift, I want you to imagine that we're going to take this hydrogen and move it over here. And so I want you to imagine that. Let's go ahead and draw how that might look. So now we see that we started off with this carbon which had 1, 2, 3 bonds. And now we graduated over to a carbon that now has 1, 2, 3, 4 bonds. Do you think this carbon is still a carbocation? Not anymore, right? And if we look to the left, we see that we started off with a carbon that had 4 bonds, so it was neutral, but now it only has 3 bonds. And so we see here that this carbon is going to be the carbocation now. So we see here that the hydrogen shifted over here, and the positive charge shifted onto this carbon here. So now we can go ahead and bring that chlorine group in here. And we can draw that arrow going from one of the lone pairs over to that carbocation here. And we see that our product is going to look like this. Where chlorine is going to join onto that lonely carbocation. And now it's not going to be so lonely anymore. So we see here that we formed this haloalkene. And in each of those examples that we did before, we formed what's called a haloalkane, where a halo corresponds to the halogen, as in chlorine, and alkene corresponds to a carbon structure that has only single bonds, a haloalkane. And so this answer here corresponds to answer choice letter A. And so the takeaway here is you want to be aware of hydride shifts. So in this video, you learn how to add HX, where X is any halogen, like HBr or HCl, to an alkene, which is just a carbon structure with a double bond. You also learn how to perform hydride shifts and alkyl shifts. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!